All right, yes, it's still morning. Good morning, everyone. I think we've got the technical issues sorted out. So to get started, I want to tell you a little story. A couple months ago, I guess probably back last winter or so, I was working on a project with one of our junior developers. And it was some existing code, and we needed to add some new functionality. And, you know, we could sort of shove it in there, but it wasn't real convenient to do that. So I started walking him through, okay, well, we can pull this out and we can make it a helper method. And we can rearrange this so it's a little more efficient and we're not having to do all these checks that we find out that half the time we're not going to need. And we're going through the project and he just turns and looks at me and says, wow, how do you even know where to start with pulling out all of these things when you're refactoring your code? And I was like, you know, he's probably not the only one wondering this. And so we're going to talk a little bit today about refactoring, otherwise known as saving your code from yourself. Because let's face it, if you've done development for any length of time, even if it's only a month, you look back at what you wrote before and go, what on earth was I thinking? So my name is Lorien. I've got all of the code examples that I use as part of this presentation up on my GitHub account. If you want to get in touch with me, you can reach me at my Gmail address or on Twitter. I even check it occasionally. So to start off with, we're going to talk about what is refactoring. And it's a word you hear a lot, but it doesn't always get defined. A lot of times it's one of those things where people just assume you know what it is and go from there. The simplest thing is, as a noun, it's a change made to the internal structure of software to make it easier to understand and cheaper to modify without changing its observable behavior, which is long and complicated, but the important bit is that this comes from Martin Fowler, who quite literally wrote the book on refactoring. And this book, Refactoring, Improving the Design of Existing Code, is, I believe, right now at the printers for a completely revised second edition. If any of you have access to O'Reilly Books Online, he's got a preview copy up there for people who've got that subscription. A little shorter definition is from Dr. Rebecca Parsons. She describes it as a small behavior-preserving change. She described this in a presentation I saw her give a couple weeks ago at the evolution of evolutionary architecture, which is amazing, but you know, it's an entire talk by itself and it's someone else's talk, so. Refactoring can also be a verb, and that is software by applying a series of refactorings, that's the noun refactorings, without changing its observable behavior. So some of you may have heard this summary of how to write code from Kent Beck, who was one of Martin Fowler's contributors to his refactoring book. Make it work. Because if you can't make it work, there's really no value to it. Make it right. Make it fast. We're focusing on the second part, making it right. So before I talk a little bit about how to refactor, I want to talk about code smells. And this is where I need to grab my notebook that I should have had out before. But code smells. A surface indication that usually, and note that usually, not always, usually corresponds to a deeper problem in the system. So we can have a couple different types of code smells. They're usually easy to spot. It's not something that you have to dig for. They don't always indicate a problem, though. Sometimes it looks terrible, and that's because it's the only way to do something. So your code smell could be, you get a smell, and it's terrible, and it's a real skunk. That's something that you need to fix. But sometimes you get a code smell, and it looks like it's terrible, and it looks like you might need to fix it. But when you dig a little deeper, It's stinky cheese. It's supposed to be that way. So we've discussed some code smells, so let's take a look at some of them. And just from the audience, first glance, what's wrong with this? Yeah, too long. This is this is why I need my notebook. This is a 61-line method, once you include all of the curly braces and the white space. My laptop, I can see 30 lines of code on it. This is one method that's way, way too long. So that's a code smell. If your method doesn't all fit on one screen, and you're at a normal sort of magnification, and you're doing a normal sort of orientation. So yeah, if you turn the monitor vertically, which is what I did to get this screenshot, yeah. Yes, you can fit it on one screen. But if you have to turn it on its side, if you have to make your magnification at like 50% instead of 100%, it's too long. Sum up from Bill Gates. I hope you all know who Bill Gates is. Measuring software productivity by lines of code is like measuring progress on an airplane by how much it weighs. Yes, a finished airplane is heavy, but you can make an airplane really heavy and it still won't fly. You have to do the right things. So here's another one that we've got some problems with. This one's a little easier to read, but it's got problems all over. So does anybody want to call out what they think might be some issues with this one? Yes. Naming, anybody want to be more detailed where the bad names are? Variables. Yeah, variables are bad. Function name's bad. I will also note this is not the worst function name I've heard of. The worst function name I have heard of is recursive function 2. That one's the worst because that's the function that, unlike recursive function 1 and recursive function 3, recursive function 2 actually works. All three were written by my brother, and I give him grief about them every time I see him. He's lucky he lives in Texas. And yes, he has given me permission to tell that story as part of this talk. And one of these days, I'm going to get him to rename at least recursive function 2 to something that actually tells you what it does and why it needs to be recursive. It does, actually. But yes, as somebody mentioned, the name's terrible. It calculates. We don't know what it calculates, but we know it does a calculation. We've got some terrible parameter names. If we had good parameter names, we might be able to guess from them, but no, we've just got a couple of random letters. And our variables aren't any better. More random letters. The best thing we can say is we've at least got data types. You know, we've got some decimals and we've got an int. So we've got comments all through this method just to tell us what we're going to do. And it's not that comments are bad, but the problem is if comments are the only way you can tell what your method is doing, you should look at refactoring that method because it's not well written. It's not what we call self-documenting code. So lots of comments, lots of names that don't tell you what they do. That's a code smell. Basically, your code needs to be easy to understand on its own without adding a lot of comments. So here we've got two sections of code. And either one by itself is probably a little bit better. But when you look at them together, we've got another code smell. So what do you see about these two?
Again, variables are ambiguous.
Variables are ambiguous, although we sort of covered that in the previous slide.
The while loops are really strange.
They're really strange. The other thing is if you look really close, we've got this temp times 1 plus r in both while loops. So that's duplicated code. That's another code smell. If you're using calling the same bit of code over and over and you're writing it out by hand every time, don't repeat yourself. Pull that out into a helper method. And then you can just call it wherever you need it. So we've got one more thing here. This is a little bit less obvious, especially out of context. But what we've got here, this is basically a guard clause preventing a divide by zero error. The thing is, z came in as one of our parameters way back at the beginning. We could have checked for this well before we did anything else and skipped a whole lot of calculations. Basically, it's just a sign that your code is badly organized. You could rearrange some things and keep all of your functionality together. I mean, yeah, if you keep all of your spare keys in a drawer and it looks like this, you'll be able to find what you need if you know all your keys are in there. Eventually. But if you've got a set of pegs, one key per peg, and you've got labels on all of your keys, you're going to find the one you need a whole lot faster. But the question is now, how do you know if it's actually helping when you're doing this refactoring? And maybe your boss is saying, we have to get this new piece of functionality out the door. We don't have time to go back and look at all this old stuff. And this, in general, makes developers want to pull their hair out because they'll go, it's wrong, I need to fix this. So how do you prove to your boss, somebody who's maybe not down there in the code all the time, that this really is adding value? Well, Visual Studio, which is what I wrote these code examples in, Visual Studio has code metrics. There are some other tools for other systems that will give you similar functionality. But these will tell you, if you run them at the beginning of your method and at the end, you can actually point to numbers that show, look, my code is better now than it was when I started. So the first one we're going to talk about is the Maintainability Index. From a couple other metrics. But it's basically, how easy is it to maintain a piece of code over time? It's calculated from a bunch of other metrics. You can Google them. The important thing is that there's even a convenient scoring system for Microsoft. So if you've got a maintainability of 0 to 9, that's in the red zone. 10 to 19, that's in the yellow zone. 20 to 100, because 100 is where they top out, that's in the green zone. Okay, who thinks this is a terrible system? Yeah, I do too. Honestly, I haven't figured out how to change their colors, but when I'm looking at my own code, I tend to look at about that 0 to 19 as red, 20 to 50 as yellow, and 50 or 100, 50 to 100 as actually being good maintainable code. Getting code of 100, I mean, you have it, but that's a lot of times that's your class definitions where all you've got is a getter and a setter, and a lot of times there's not even a whole body to them. So I mean, that's maintainable, but you generally don't have to do a lot. For actual working code, a lot of times I can get stuff in the mid-60s pretty easily. And that's reasonably maintainable, not too hard to add stuff to and change when it's needed. So maintainable software, it lets you fix bugs more easily. I know we don't like to admit that there are bugs in the code, but sometimes there are bugs in the code. And it's a lot easier to fix if the code is well organized, well maintainable. Something we're happy about, adding new features. If you've got maintainable code, you can add features more easily. You don't have to look at that 60 or 100 line method and figure out, well, where do I stick this in? Where does it even fit? Does it even fit? And since your bugs and features are a little more easily taken care of, that means you have more time to spend on brand new work, which is always fun. Work on something new and not the same thing over and over. The next one we're going to look at is called Cyclomatic Complexity. And that's the number of distinct paths through a method. Some methods, they just transform something from one state to another. That's a very low cyclomatic complexity. But when you get into if statements and switch statements, where you have a lot of different paths to get your outcome, those tend to have higher cyclomatic complexity. So this is a very low cyclomatic complexity. It's a sum function. You add the first number to the second number. There's only one way in and out. So that's got a cyclomatic complexity of 1. This one's a little bit more useful as a function, basically. Second is greater, return the second, otherwise return the first. 2 choices. This one's more moderate. It's a cyclomatic complexity of 6. And this is a variant of some code we actually use at my office. The idea is that given a language, tell me which one that I am supposed to be using. Since these are strings, they could all potentially be null. They could be a language that's not on that list. What if you have one language and it's German? That would fall through all of these and go down to English. But basically, you have 6 paths through this code. And this one, don't even try to read it. Really, just don't. But this is from a kata called the Gilded Rose, and one of the things it's designed to demonstrate is the helpfulness of refactoring. Another one is it's also useful for teaching unit tests. This one, when I ran it through Visual Studio's code metrics, came back with a cyclomatic complexity of 21. Usually you want to keep your cyclomatic complexity under 10. And even that is kind of a lot. So that 6 method one, or the complexity of 6, that's not too bad. Especially for something where you've got a lot of analysis on one small set of data. Something like this, I've done this kata, there's no need to have one method that's this long with 21 possible paths through it. The last thing we'll look at is lines of code. So this is not like that 60-line method we saw earlier, because this is only referring to executable code. It does not refer to white space. It doesn't refer to comments. You can't execute a comment. You might want to, but you can't. And it doesn't count curly braces when they're on their own line. Those are just punctuation. They don't actually contribute to how the code works. More lines of code, more code to maintain. So that's why this is part of these code metrics. That said, code metrics are more useful when you're looking at them on the method level as opposed to the class level. And when you get to the project or the solution level, Visual Studio will calculate those for you. But they're not really helpful, because you might have a very large object that's just got a whole list of properties. That could run several dozen lines of code and have a very low cyclomatic complexity for each of those, because each property is one line, one path through it. So it's not really valuable once you get above the method level. So this is the original code metrics from the sample we'll be walking through. It's a pretty simple exercise. It is, in fact, a interest calculator for a mortgage. So that's a known math problem. It's not that complex, but we've still got a maintainability index of 49 because everything's in one method, and a cyclomatic complexity of 6. And those 60 lines, 26 of them were executable. So here's our start. We've got those terrible, terrible names. So the easiest thing we can do here is we can rename everything. We're calculating a monthly payment. Y is short for years in mortgage. We have an annual interest rate, better than AR. And then we've got better variables. And the other thing is we no longer have comments. We know this is our monthly payment because it says monthly payment. We know this is the amount financed, principal financed. We know this is our monthly interest rate because it says it's the monthly interest rate. And we know this is the number of months in the mortgage because it says it's the number of months in the mortgage. We don't need those comments anymore. It didn't affect our code metrics at all, but it's a lot easier to read. The next thing was that duplicate code, where we had this temp equals temp times 1 plus r, and we've got two while loops that are kind of funny looking, but really do the same thing. It just changes where we're doing our I++. Couple different terrible variables. But we can pull them out so that now we have a helper method here. Raise decimal to the power of the term. We need to use it in a couple of places. We call one method, get this same functionality. And here's where we start seeing the value of the code metrics. Our maintainability on that original method just jumped by 6 points, and our cyclomatic complexity went down by 2 points. And we lost 10 lines of code just by pulling that out. Even more dramatic when you look at it as a graph. One of the nice features of Visual Studio's code metrics, and I'm not sure which of the other tools have this, is you can copy directly to an Excel file and then pull out the lines you want. And once it's in Excel, it's very easy to make a graph. If you've got to convince somebody who really likes looking at charts and graphs, well, here's a graph. And you can show some good trends right there. It's more maintainable, less lines of code, less complex. So the next thing we want to do is, okay, we've got that helper method now, but really that's just a helper calculation. What you can do is also pull out some sub-methods. We've got a numerator power and a denominator power. We can pull out some helper methods, one to calculate the numerator, and that's all it does, is it calculates the numerator in our monthly interest rate calculation. And another one that calculates the denominator in our monthly interest rate calculation. Each one does one very specific thing. That's something to keep in mind when you're extracting the method, is if you've got a block of code, you need it, it has to look like this, but it does one very specific thing. That's a place where you can consider a helper method. This is not figuring out the numerator and the denominator at the same time, which means they're good cases to be pulled out. You're not sharing anything, you're not sharing any of the results between them. They're just two things that you calculate. That doesn't give us much of a bump because these particular methods weren't really complicated. If, on the other hand, your I need to figure out one thing is kind of complicated, for example, in the cyclomatic complexity example, when we were determining which language to use. If you pull that logic out into its own helper method, that'll give you a noticeable bump in your metrics for your main method. We're skipping the graph because there's really nothing to see on that one. But the last thing we've got here is to reorganize our code. So we've talked about how this z equals 1, we have to prevent a divide by 0 error, which means we don't need all of these other calculations. X and z are our numerator and denominator values. Well, we don't really need to go through all those calculations if z equals 1. we've got 1 year in the if we have no years in the mortgage, we can just return our principal financed without needing anything else. That's your payment. We're not loaning you this for any length of time, you just owe us money. The other thing is if your annual interest rate is 0, we don't need to do any interest rate calculations. There's no interest rate. Your monthly payment is just how much did you finance and how many months are you paying it off. So that's another guard clause. So we can get all of that taken care of before we jump into calculating our monthly interest rate, calculating our numerator and our denominator value, and then figuring out our monthly payments from those. So yes, guard clauses, if you've got something that you know in this case automatically returns you something, do that as early as possible as you can in your code. Don't worry about figuring out the rest of this. That gives you a quick and easy escape route. Take those when you have them. And that gave us a bump in our code metrics as well. It doesn't look like a lot, but our maintainability is up by another point, and our cyclomatic complexity is down by another point, because now we've got that escape route. We're not running through if logic that we don't need to run through. And it reduced our lines of code. So this change was a little bit more subtle than the last change, especially on the maintainability, because it was already such a high number in comparison to the others anyway. But we've still got a noticeable trend, and the trend is in the correct direction, no matter what. So that leads to the next question of, well, when should I refactor? And I'm seeing these in my code base, but you know, I've got these bugs to fix. I've got this list of new work that needs to be done, this sprint. I've got these features that need to be added. I can't take a whole sprint to just go in and refactor my code no matter how much I might want to. First thing is what's called opportunistic refactoring. If you're already working in a block of code and you can see where you can clean it up a little bit, go ahead and make those small changes. You know, you've got a terrible variable name. Rename it. That changes no functionality. If you miss it in a spot, it probably won't compile. There are some plugins. There's one that I use called ReSharper that will allow you to just pick something and automatically rename it. It will find all instances of that variable, rename them the same. No spelling errors, no missed variables. It's very convenient. The other thing is follow the Boy Scout rule. Leave it better than you found it. You're in a piece of code, you can see these small changes that will make it work a little better. Make the small changes that make it work a little better. Leave it a little bit better than you found it. Now, to make sure that these all work, generally this is assuming you have unit tests on the code in question, so you would make your change, run your unit test. If the unit test still passes, it's a good change. But sometimes, especially in older code, you don't have unit tests. Sometimes that's going to stay that way, and sometimes it's not. So if you don't have unit tests, and you're in a project structure that allows for them, you're starting from a blank slate, write the tests on those. You've gone from, you know, maybe you go from no tests to 1 test. That's still more than you had before. And then you can refactor the code that's around there a little more safely. Maybe you've got testable code, but it doesn't have tests. It's long and complicated and you can't figure out what all the results are supposed to be. But maybe you've got that one clear path. Write a test or 2 on that one clear path. You've got other paths. They're going off in weird directions. They're taking strange loops on the side. Don't worry about them at the beginning. Just a little bit is better than nothing. And sometimes, maybe it's the project structure, maybe it's a time constraint. You're not going to be able to write any unit tests. In that case, you can do what's called a smoke test. And this is used in a couple of different ways. You'll find it in infrastructure, for example, sewers, pipes, things like that, they'll literally pump the pipes full of smoke, see if it escapes anywhere. The other thing is place it comes from is hardware, where if you've heard of the magic blue smoke that escapes, basically you have some idea of where it works, where the state is at the beginning, the state is at the end. You run through it in a normal situation. If that works, you've got a smoke test. You know at least the happy path works. You may not know why it works, but you know it's there. It worked before, it works now. None of the smoke has escaped. So at this point, are there any questions? Yes.
You said those metric tests were available in Visual Studio.
Yes.
Do you just access those through the
In the
test
tool,
menu?
actually they're in, I believe they're in the tools menu. I would have to actually pull it up and look. The one thing is that they don't seem to have got them exported for .NET Core yet. If you're working in that, there is a plugin, Ndepend, that will provide you with, actually I think more expanded functionality, but it includes all the metrics that we talked about.
Thank you.
Yes?
Do you have any sense for how the maintainability score is computed?
I looked it up and I was like, okay, yes. I think this makes a lot of sense and half the math is going over my head. It is a function of, among other things, the cyclomatic complexity and the lines of code, but I think there's a little bit more to it as well. Anything else? Yes?
So in your company, is it common to check those metrics on the code, or is that just something you do?
It's in and out every now and then, especially when it's a little bit slow and I know I'm refactoring something. I will keep track of my metrics on it from start to finish. It's not an always thing. The other thing is we'll also use them in the case of that opportunistic refactoring. I'm in this code anyway. It looks a little funny, but I'm not quite sure. We'll run the code metrics. What do they say? Is everything in a good state? Let's leave it alone in the interest of speed. But oh, okay, that's got a maintainability of 30 or a cyclomatic complexity of 8. Let's see if we can clean that up a little bit. So they're good for making that sort of decision when you're sort of on the borderline. Any other questions? Okay, well, there are some other resources. Martin Fowler, as I said before, he's got his own website with a lot of stuff on refactoring. The second one is actually the link where he discusses everything that's been going into the second edition of his book. And it's got the link to the preview copy on O'Reilly Books Online there. Sandy Metz has a really long example of refactoring using the song 99 Bottles of Beer on the Wall. The idea of take a function that would spit out the entire lyrics of the song and do it efficiently and in a well-organized manner. Ardalis, otherwise known as Steve Smith, has a very nice article on when you should refactor on his blog. He's also got a course on Pluralsight, which I admit I have not taken yet, but I have worked with him in person on some of this stuff, so assuming he's covering the same topics, that should also be a very good course on just getting into the fundamentals of refactoring. I mentioned some other tools. Ndepend, in-depth metrics, and it does cover the .NET Core stack, which the built-in Visual Studio metrics do not. JetBrains, they have quite a lot of tooling. They've got some IDEs of their own for a variety of languages, some of which do have built-in metrics. They also have, if you're using, I know for .NET, and I think maybe at least one other language, a tool called ReSharper. That's the one I'm using when I'm renaming stuff, because it will cover things not only at the method level, but if you are, say, renaming a class or renaming an external method that might get called from other files, it will go through your whole project and clean that up for you so things don't get lost. it is really amazingly helpful. And again, my information, all of these code samples are up on my GitHub account if you'd like to check them out. I'll also be putting a copy of these slides up there this weekend. A slightly earlier version is up there. It doesn't have all the resource links that this one has. And I will put something out on my Twitter when those slides are live, so that if you follow me, you'll be able to get the link to them that way. That is it.